Average rate of change. That's true. Difference quotient. But how did we write it last year? Average rate of change of a quantity f. F of b minus f of a all over b minus a. That's if you're given the quantity whose rate you're trying to find. Yes, there was a different formula if you were given the rate and you were trying to average the rate that you were already given. Had to do with accumulation integrals. But this is when we're going over some sort of change in time. Hence the, what's this line called again that cuts through a graph? Secant line. Hence the secant line. Quick reminder of intervals. But instantaneous rate of change, that's where we're going with the slope of the tangent line. That's where we would technically, by definition, you guys apply the definition of the derivative. Oh, I already did it for you. What would you plug in to finish the definition of the derivative? Yeah, it's just instead of x's, you're going to have t's and delta t's instead, right? So an arbitrary removed y minus the point of tangency y all over the delta t, the change in t. So super similar to delta x, just with t's instead, because we're talking about rates of change to begin with. Why do I have h's down below? Yeah, because some people with the delta t, they start to get confused and try to put the t and the delta t together, and then it just gets confusing. Delta t squared isn't a thing. Anyway. So down below, very, 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 very similar to up above. The limit as h approaches 0 of 16 times 2 plus h squared minus 16 times 2 squared over h. What does it represent? Let's start there. What's going on if you do solve this limit problem? How to solve it? How is it going to solve for you? What's the final solution going to be? What are the units of the final solution going to be? Feet per second. And so wait, think about our motion. There are three big concepts: position, displacement, etc. Position, velocity, and acceleration. Who is it? Instantaneous or average? So we're finding the velocity. We don't have to say instantaneous. We can just say velocity at, where is it at? Keep going. 16 is part of the function. Careful. That has to do with gravity. Falling is indicating the negative. And so this is half of gravity, half of acceleration. T squared comes from the integration of going from acceleration to velocity, velocity to position. There was that formula last year. The physics kids, last year, because we don't have physics this year, physics would have memorized this formula. It was an important one for position. And we saw it a little bit. But gravity is negative 32 feet per second squared. Divided by 2 is 16, negative 16. But they said falling, so that's the negative. So yeah, 16 is just because of gravity. That's all he is. When or at what time from here are we solving for the velocity? Not 0. Louder. 2. Why? They plugged in 2 for the x's or for the t's. So at 2. So we're trying to find velocity at t equals 2, which would be the same thing as x prime of 2. This is the definition of the derivative when t is 2. Do you see it? There you go. Remember in the AP, for those of you that took it with me last year, how they would give us sometimes a limit problem that looks like the definition of the derivative, and we didn't have to actually do the limit stuff that Riley was saying in the sense of foiling and simplifying and canceling out the h's and then plugging in, but instead we could actually do the derivative itself. So how can we shortcut this whole process since it is just a derivative? Take the derivative of y equals 16t squared and, oh, hey, sweet, velocity is the same thing as 32t. I'm trying to do it such that t equals 2. So therefore, how fast is it falling? And why am I going to make sure to make a point of putting the word falling? Because it's going a negative velocity since it's headed down. Except the question itself said falling. So that's the dilemma. Because if they go ahead and, if they're sticklers, they'll say falling a negative? No, that's rising. Like, wah, wah, wah. So the representation of this, instantaneous velocity, because the distance between the 2 points, the secant lines are getting close to the tangent line. We could solve that limit by foiling and simplifying and plugging in 0 at the very, very end once the h's cancel out. Or we could just take the derivative with the power rule, plug in, and be like, done. Dun, 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 dun. Ironically, that was their introduction to limits. Go figure. We did use our calculus knowledge to do it in a shorter, sweeter way, but speaking of limits and limit definitions of derivatives, this book is a little interesting in the order sometimes. But that's okay. In college, sometimes things will be in weird orders too, and you're like, okay, well, can't do anything about it, but just go forward. One-sided limits versus two-sided limits. It's a little bit messy, I apologize. It's kind of like in the quotation marks. So when I say A with a little negative and A with a little positive, just a quick reminder, I'm talking about X approaching A, right? And X approaching A. And when I'm saying A with a little negative, what am I talking about? Numbers that are a little bit below. Good. Good. And so below, I could say from the left. I could also say from below. Just because I used the example last year, and I'm using it again this year, even though the videos didn't work, about the two guys in the cars who were trying to meet for breakfast. I also started using this year, thinking it might make it a little bit more concrete in their minds. I could say from the west. The west side of the point, the west side of the meeting point. Or I should say the meeting time, if we were talking about that. From below, like on the number line, from below, from the left, from the west, if you're thinking about the actual location on a graph. As X approaches A positive, now I'm coming from the, let's just do all the opposites, right? From the right, aka from above, aka from east. One-sided limits, you can approach from just one side, just from the west or just from the east. The example with limits. Just thinking about where the driver on the left is headed, or just thinking about where the driver on the right is headed. Remember, limits, the answers are always what kind of values if you're on a graph? Coming from the left and right of an X, but what are you looking at for the actual limit? Y values. Good. Let's see if you guys have had me long enough to be able to perfectly fill in the statement at the bottom. The two-sided limit will only exist if perfect. The one-sided limits agree. I think we hit that one pretty hard in honors last year too. Honors pre-cal. The limit will only exist if the one-sided limits agree. So if, as you approach the X value, which is a vertical line, as you approach that X value from below, from above, from the left, from the west, from the east, are both branches approaching the exact same location? The dilemma is a whole, not because it's hard, but because it tricks people so much of the time. But we'll get there. A couple more seconds, we should be close. What's the notation for two-sided limits? So that one's from below, that one's from above. How do they denote coming from both sides, how they have to agree?
So they're just
Exactly. There's nothing. It's just the limit itself, right? So if the limit additionally has the minus or the plus, it's talking about only one side, only one approach. But if there's nothing, it's understood to be a two-sided limit. Good, good, good. Okay. Ready, set. You try it on your own first, and then once you have answers for each and every one, turn to your group and grade it, and let's see if we agree or not. No, but then in our notes we should have a nice copy of the sketch, because then life is a lot easier. I mean, the good news is you guys collaborated, like you were able to use each other. I guess you could have gone and Googled something. Issa's group, are we going to give him grace and take it? All right. We're going to face palm a few more times, but besides that. Silly goofs. Pause. Wait, you need a good sketch of the graph to be able to use it, right? I'm going to help you. First quadrant. And if you haven't started doing the graph yet, I'll give you the points. Do what I tell you to do. Ready? Can you follow directions? Draw a graph. First quadrant. I'm going to give you the points. Do what I tell you to do. Ready? A point at 0, 1, filled in. Linear function down at 1, 0. A point at 0, 1. Draw a line down to a hole at 1, 0. A filled in point at 1, 1 with a horizontal line over to 2, 1. There's a hole. Filled in point at 1, 1 over to a hole at 2, 1. Linear function. There's a filled in point at 2, 2. Or 2 equals 2. Going from 2, 0 up linearly to the point 3, 2. There are no more holes. The point at 3, 2. The linear function down to 4, 1. There you go. Okay, I'm going to pause. 2 minutes. Oh, look, it's a piecewise function. See, piecewise functions aren't that scary. So if you finish early, you can think about the definition of continuous. Where is the function not continuous, and what points of the definition defend that or prove that? And or if you have some extra time, what if you did not have the picture? Could you have, from the piecewise function, figured out the limits that were being asked of you? Okay, collaborate. Some of you guys have been way too quiet. So either you haven't checked with each other, or you haven't done it well, or you've taken a little bit longer than maybe you should have. Talk it through real fast, wherever you are. It's okay, talk it out. my turn. Can you fill in the second statement? Ah, the first statement, yes. Second statement, no. But you're right, the one-sided limits do not agree. That's why this one doesn't work. F of 2 does not equal the limit. You guys agree? The limit does exist. It was 1 because the one-sided approaches did agree. The problem is the point wasn't there. So the function's not continuous, but the limit did exist at 2. Now, for those of you guys that aren't super strong on taking limits of piecewise functions, can I, in some way, shape, or form, cover this guy up entirely? Well, it didn't really work so well. Cover that guy up entirely, aka, there we go. How can you defend for me why the limit as x approaches 1 from the left of f of x is 0 from the function? Left of 1 is less than 1. Left of 1 is less than 1. What piece? Plug it in, negative 1 plus 1 is 0. Got it. 1 above, greater than 1, right? Where's greater than 1? Plug it in, plug it, 1. Compare the two. Oh no! 1 is in 2 different pieces. Approaching from below, approaching from above. Exactly. Test them both. 0 and 1 do not agree. But 2. Oh no! 2 is, wait. But that's not approaching. That's at, right? Well, forget him. 2 below and 2 above. Okay, 2 below, plug in 2, it's 1. 2 above, plug in 2, it's 1. Ah! 1 equals 1. Done. Limits. You don't look at the at. You look at the below and the above and compare. The at. Dun, 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 dun. Is it? No, they don't agree. Okay, cool. Did you need the graph? Nope. If you needed the graph, get really good at graphing piecewise functions fast. Sad day. Okay, let's keep going. Just lines until it starts getting to be like e to the x's or trigonometric, or I mean, they could put all sorts of stuff. Oh, such a struggle. Here, hold on. There. Wait a minute. Do you guys necessarily need to write all this stuff down? No. What do you need to do? Finding the limits. First, plug it in. How do you shorten this entire page? How to find limits? First, plug in. The limit as x approaches c of f of x is f of c. You're done. Many times, I'm just saying the majority of the time it works. Our book goes through, maybe I go through. No, I think our book goes through. It's like, hey, polynomial functions, it's going to work. Rational functions, it's going to work as long as q of c does not equal 0, right? If you plug in and the bottom equals 0, you should think 2 things. 0 over 0, keep going, or number over 0. Infinity? Question mark, Danny? I'm not quite sure. Some of you guys, summer review quiz? The one where as you approach 0 from the left and from the right, one way was positive infinity, one way was negative infinity, and so therefore the whole thing did not exist. And it was both. Struggle. Yes, please.
I was like doing some calculus like the other day, and my mom came over, and she was like, "Oh my gosh, you write your S's so cute," and it was an integral stuff. I was like, "Oh my gosh." I was like, I know.
Oh my God. Just let her see your sigmas. She'll be like, whoa, Sami. It's okay. My mom would probably do the exact same thing. My mom, when was this? It was when one of the newer Star Wars movies was coming out. I think it was a few years ago, though. Yeah. She was like, well, I know that she's never watched any of the Star Wars movies. She's like, I know that there's like this guy in black, and I don't think he's good, but and then there's like this little creature thing, and she didn't know any of the names. I was like, Yoda? I don't know. We're walking through Kohl's, and she's like, oh, isn't that? I'm like, yeah, I'm like backpack and stuff. Like, Mom, Star Wars movies have been out since the... Anyway. Good times. But give her a musical, she'll be good. Doris Day, Audrey Hepburn, no problem. Star Wars. So basically, guys, all these functions are good, right? Unless they're not. Go team. So which ones couldn't be? Rational, denominators look out for. Radical, what could be a problem? Yeah, I guess if they do something outside the domain, but isn't that super awkward? Like, why would they do something outside the domain? Yeah, they probably shouldn't do that. Composite functions. This one's a property that we typically don't think about, and every now and then it stumps us on an AP question. Where, to take a limit of a composite functions, you can sometimes you have to consider a few things like the domain of the inside and then how the domain of the inside maps to the domain of the outside. It gets a little nasty every now and then. Usually doesn't trip us up, but we can take, as long as we are continuous at of the inside and the outside at the inside. We can bring that limit in. We can think of the square separately. We can think of the ln separately. We can think of the e to the separately and just take the limit of the inside first. It does make life easier sometimes. Yes. But depending on what's given, there's been a few times last year that it tripped us up. And I was like, wait, this is a property. We can do this. I just remember it. Not the specific example, sadly. Trigs, you need to watch out for vertical asymptotes for everything but sine and cosine. Why is sine and cosine limits never a problem? Because they're continuous. But the dilemma, will sine and cosine be a problem with limits? Not if they're coming towards a point. They're continuous everywhere. No vertical asymptotes. There's a S and L. Never mind. So anyway, yeah, if you go to infinity of sine, you're in big trouble because it just oscillates. If you oscillate between two values, are you going towards one single value? No. So the limit does not exist for sine as you go to infinity, or for cosine as you go to positive or negative infinity. Then you have like your a to the x, your ln of x, your inverse trig, all your other transcendentals, but we can deal with those. Moving on. Keep going. How? Try to plug in. As long as it works, you're good. Watch out for domain problems and watch out for discontinuities. Test around holes and vertical asymptotes. 0 over 0, keep going. I just threw it all in like one big old page. You don't need me to go through and show you each of them. Why? What are we going to add to this list of... It sounds really nice, though. James is just shaking his head at you all. He's way too gracious for that. I'm shaking my head at you all. Are we good? Oh. Should we ever have to worry about synthetic or long division? No, because if you can't factor it, what are you going to do? When you say things wrong, they don't come out right when you need them to. L'Hôpital's. Okay, pause. Shh. Crazy hospital infection. Are we good? We need a mission trip to like Canada. Then our Frenchies can go. Not just L'Hôpital. In some ways. In other ways, just stay over there. But you guys see how this is all the different keep goings, right? There technically is one other. Technically. I'll say L'Hôpital's, or why am I going to say special limits? Yeah, and even with those properties, you can use L'Hôpital's too because it's 0 over 0. But the sine of u over u, limit as u goes to 0. 1 minus cosine of u over u, limit as u goes to 0. So technically the special limit into this keep going category also because they'll give you 0 over 0. Ah, but what if you plug in and get number over 0? We've talked about it. What kind of form is it? Infinite. That one's indeterminate. Indeterminate. I don't know. Keep going. Infinite. We're done. It's a vertical asymptote. We're not done. What am I going to say? Positive or negative infinity. Check the sign. And maybe we should add this for the quiz. And compare the one-sided limits, yeah? Don't just check the infinity or check the sign from one direction. And compare. It was hard on the quiz. It wasn't easy. It wasn't one that I could answer in 30 seconds when people asked me. I would have had to actually think about the estimates of e to the. It all came back to. You guys good if I go forward and keep that one? Oh, that's no fun. I want space to do an example. Does anybody have their summer review quiz? Yeah, we need to turn those corrections, huh? Let's turn them in Monday, right? Okay, what was that problem? The one I'm talking about is the limit where you got a number over 0. It was the second limit problem, I think, B. Was it limit problem B? With an E in it and a fraction? Limit as x goes to 0? My brain didn't go there fast enough when you guys asked me over the quiz. But here's the dealio with e to the x. Isn't e of 0 1? So if e of 0 is 1, then question, what would e to the a little bit under 0 be? A little bit less than 1? What's a little bit less than 1 minus? Oh, that's a negative number. What's e to the a little bit more than 0? More than 1. Oh, that's a positive number. Negative infinity, positive infinity. What's going to happen? At that vertical asymptote. Why is it a vertical asymptote? Because it's number over 0. So I have a number over 0. I knew that there was a vertical asymptote at x equals 0. The struggle was I needed to check the sign. As I check the sign, if I have negatives coming in and I have positives coming in, my limit should not have existed. Yeah. Yeah. But if you think about the basic graph, you can think, oh, a little bit under 1, a little bit over 1. I know. Struggle, huh? And we talked about special limits, so I just had the special limits here. I'm not going into all the different trig and exponential and logarithmic. We talked about exponential will help as far as having a reference point, like with ln or with logarithms, specifically ln. What's the point that I can use with ln? Not 0, 1, 1, 0. I can use that one. So when x is a little bit more than 1, then ln is going to be positive. X a little bit less than 1, ln is going to be negative, etc., etc. Oh, look, I'm done. This is forever number 3, I think, right? Forever number 3. So for those of you guys that are coming into my class, I need to share with you, I need to actually send with you the forevers from last year. Actually, I'll put them in our class folder under class notes, last year's Forever cards. By this section, you're going to want Forevers 1 through 3 copied down. But I will go ahead. I have like a Google Doc of all the different Forevers from last year. So most of us are just doing section 2.1 for Monday. It's already posted in Google Classroom, I think, as of 8 a.m. this morning. I put it on like a schedule-y thing. Kind of cool. But for those of you who skipped into BC, check out the class notes folder. Email me if you can't find it, Forevers 1 through 3, and I'll see you guys later, Gators. Yes. Over here. Sorry, Gary. Oh, stapler's right, if you need it. Oh, I meant to collect it and I forgot, so we'll do it Monday when you get corrections. Summer review quiz. And then you'll get this one when you take the quiz.
The quiz. Yeah, I was like, wait, I didn't that. But also, I have to talk to Mr. T.